You might think the absolute biggest threat to theoretical science is, I don't know, bad math, or maybe a flawed experiment, but actually it's not. The most dangerous trap, the thing that can completely unravel a brilliant theory before it even gets off the ground, is everyday vocabulary. Literally, just words. I mean, really think about it. What happens when a grand, complex theory of the universe uses everyday words but means something completely different by them? Today, we're looking at the Information Manifold Model, or the IMM for short. Now, this is a seriously fascinating theoretical framework. But early on, the IMM ran into a massive wall. By using words like information or projection or consciousness, the framework risked collapsing before a reader even finished the first axiom. Why? Well, because, let's face it, everybody brings their own personal baggage to those exact words.
So welcome to this explainer. I am genuinely thrilled you're here because today we're taking a truly fascinating look at the behind-the-scenes architecture of scientific rigor. We aren't just looking at what a scientific theory claims, we're looking at how it literally forces itself to be honest about those claims. This is all about the anatomy of scientific honesty.
Okay, let's dive right into this. Here's our roadmap for today. We'll start with 1, the problem with words, move into 2, locking down the vocabulary, explore 3, the danger of overclaiming, then 4, mapping the unknown gaps, and finally, 5, the anatomy of rigor. Kicking things off with Section 1, the problem with words, and specifically the danger of semantic drift. So semantic drift is this incredibly sneaky phenomenon where readers, and honestly, sometimes even the authors themselves, accidentally substitute their own colloquial meanings into highly technical writing. Let's take the word information. The plain, everyday definition is basically just linguistic content, right? Like the meaning written in a book. But the strict IMM technical definition is a relational structure on admissible states capable of affecting a receiver. So in the IMM, a book actually doesn't contain information without a receiver. It's just a raw pattern. If you read the theory using the everyday definition, you completely misunderstand the physics. And honestly, this is exactly how brilliant academics end up in brutal fights over dictionary definitions rather than debating the actual science. Which brings us to a really brilliant quote from the foundational text by Travis Bergen. He says, "Without a fixed vocabulary, critique attacks ghosts." If we don't completely lock down exactly what our terms mean, critics just end up attacking a strawman version of the theory. They end up attacking claims the framework literally never made, and that is incredibly frustrating and just a massive waste of everyone's time. So how do we actually fix this? That takes us to Section 2, locking down the vocabulary by building a solid lexical foundation. The IMM completely solved this semantic drift problem by creating a lexical foundation that's treated like a strict binding contract. Every single term goes through a mandatory 3-part definition format. First, you have the plain definition, to just sort of anchor the reader. Second, the IMM technical definition, which establishes the precise framework-specific meaning. But the third part, and this is absolutely brilliant, is the explicit non-claims. This specifies exactly what the term does not mean. By doing this, it proactively defends against those strawman arguments we just talked about. It explicitly closes the door on bad interpretations right out of the gate. But wait, it goes even further. There's a 4th clause for what the framework calls high-risk terms. We're talking about heavy words like consciousness or projection. These terms get an operational consequence clause. This defines the exact specific checklist that a claim absolutely must satisfy to use the word validly. It basically turns the dictionary from a simple reference guide into a legally binding scientific contract for anyone writing within the framework. Moving into Section 3, the danger of overclaiming, and why we absolutely must police epistemic operators. Okay, so the absolutely crucial point here is understanding what an epistemic operator actually is. These are terms like derivation, emergence, or isomorphism. Basically, they're the words used to state exactly what a framework claims to have definitively proven or established. Overclaiming a result, like saying you derive something when you really only exhibited an example of it, is pretty much the deadliest sin in theoretical science. It is exactly how theories lose all their credibility overnight. Let's take the word isomorphism. Now that is a massive claim. It means a mapping preserves all specified relational properties perfectly. But after some rigorous testing between cosmic and cognitive dynamics, the framework's authors realized they couldn't actually support that. So in an act of just radical transparency, they downgraded their own claim to a correspondence, which only preserves some specified properties. And actually, it goes even further than that. The framework's author literally withdrew their own 13th paper entirely? No way, right? But why? Because paper 13 improperly claimed a derivation of a concept when, upon strict lexical review, it was actually just an exhibition of standard math. Instead of just leaving it up and trying to defend it, they pulled it from the archive completely until it could be lexically compliant. I mean, that is an astonishing level of dedication to intellectual honesty. All right, section 4, mapping the unknown gaps and creating a blueprint of the unknown. You see, a mature scientific theory doesn't sweep missing math under the rug. It actively uses a gap ledger to explicitly categorize what it doesn't know. Think of it like a ladder of confidence. At the very bottom, you have an open question. That's a problem with no current answer and no clear route to one. Moving up a step, you have a pathway identified, where you know the route, but, well, you haven't done the math yet. Higher still is a conjecture, then an ansatz, which is an explicit assumption, all the way up to a fully proven theorem. The rule is simple. If your claim is just an ansatz, you absolutely cannot label it a theorem. This ledger actively tracks massive vulnerabilities. Take gap 4, for instance. The IMM relies heavily on the concept of physical projection, but gap 4 openly admits they don't yet have the canonical mathematical definition for the physical projection operator. They list the domain, they label the current status as an open problem, and they literally map out the exact resolution pathway required to fix it. I want you to really consider how powerful this philosophy is. A framework is stronger when its gaps are explicit, classified, and paired with resolution conditions. By loudly documenting their own blind spots, they turn their failures and missing links into a completely actionable, transparent roadmap for future scientists to solve. It's brilliant. Which brings us to our final stop, Section 5, the anatomy of rigor and the checklist for future claims. To make absolutely sure no future papers slide back into bad habits, every single claim must pass a really strict step-by-step checklist. Number 1, what specific object is being discussed? Number 2, what exact projection operator is used? Number 3, what structure is preserved, and crucially, what is lost? And number 4, what would actually falsify this? If an author cannot answer these 4 questions clearly using that locks-down dictionary we talked about, the claim simply cannot be published. End of story. And the rigor doesn't just stop internally. True scientific rigor also requires looking outward. The ledger demands that you actively seek out rival models. If you make a claim, you have to state what rival model could produce the exact same result. And then you have to explicitly define what makes your framework distinct or more specific than that rival. If you can't beat the rival, you just have to admit your claim is generic. So this explainer isn't just about the information manifold model. It's really a masterclass in how to think clearly. We've seen how defining our words, rigorously policing our own claims, and loudly mapping our own ignorance creates an unshakable foundation for truth. So I'll leave you with this final thought. If a grand scientific framework is ultimately only as strong as the gaps it is willing to admit, what gaps are you hiding in your own thinking?